Okay. And there's no microphone I should be using. I should just talk. You guys hear me okay in the back? You guys alive? Yeah, okay. Cool. So yeah, thanks for the introduction. Thanks for having me here. So I'm going to talk about a project that we have on assessing the economic rationality of large language models. And I guess the first thing to ask about that is, why and what do I mean by that? Oh, no, the first thing to ask about that is who did the actual work? So these people, so Narun and Taylor are my two PhD students. Yoav Levine and Moshe Tenenholtz are colleagues of mine at AI'21 Labs, where we all are. Let me make this go away. Okay, we're all working at kind of a large language model startup, and Shmuel is a PhD student of Yoav Levine's at Tel Aviv. The paper is on archive and just about to appear at ICML, except for the last part that I'll tell you about, which is brand new stuff that has never been presented until today, and we'll see how that goes. Okay, so the classical kind of dream of AI is to build agents. And here's a picture from Russell and Norvig 2009. I could have found a version of this picture in all kinds of different places, but without the handsome little legs made out of ellipses. That says, you have an environment, the agent perceives the environment, there's this box inside the agent that performs some kind of reasoning where it makes plans and it models the environment, and then ultimately optimizes some kinds of preferences to take actions, which then change the environment, and the thing cycles. And the kind of view that we've had of what an agent should look like on the inside in kind of classical AI has had all these modular pieces that I've just described. So we would build kind of planning, and we would build some way of representing preferences and reasoning about preferences and maximizing something about them. And all of this has the advantage that you can decide whether your agent is ready for prime time, whether it actually can be relied upon and does a sensible job of taking agency and acting on your behalf by kind of looking at how each of these individual pieces is built and works. There's now kind of a crazy new possibility that is coming on the scene, which says, never mind all of that. Never mind representing the environment and carefully reasoning about sensors and expressing preferences. What if instead we were just to describe the world in text, hand that description to an LLM, and ask the LLM, you're an agent, what would you do in this situation? And then have it in text say what it would do, translate that into action, update the description of the environment, and on you go. And so you see, as is typical in LLM work, that there's an absolute flurry of activity on this topic, and that all of it was in 2023. So people are just starting to think about it, typically in pretty small, sort of sandboxed kinds of environments, planning, some problem solving, some kind of tool use, and being connected to video games like Minecraft and other such games. So I think it's an exciting direction. The real caveat about this direction, though, is that it's hard to know anymore whether you can trust this thing to be a good agent. Because before you could say, does it maximize its utility function? How well does it solve the planning problem? You could sort of open up each of those boxes and see what they did. And now you don't even have boxes, right? You just have this inscrutable, godzillion number of parameter black box that just takes text in and text out, and it doesn't really have these individual pieces. It's not even really clear whether it consistently has preferences, let alone what they are, whether they're responsive to the prompt they're given. So let me illustrate kind of what our dream is, the co-authors of this paper, and also the kind of current challenges in the state of the art. So let's say that I was to give an LLM a prompt like this. You're at the casino and on a losing streak. The past two hands, you've lost 5,000 and change and 1,000 and change. How much have you lost in total? We hand this off to GPT-4 Turbo, and it says, It knows how to do a chain of thought reasoning, so it starts blathering on even about the simplest thing. It says, well, to find out how much you lost in total, simply and there you go. It can solve a problem like this. By the way, I'm going to show you throughout this talk all kinds of little examples like this. You're going to have to trust me that we've done this many, many times, and that everything I'm showing you is representative. So I'm not cherry picking examples either on the positive or negative sides. So far so good, but that might lead you into a false sense of security that GPT-4 Turbo is good at problems like this. Here's another version of the problem where we added some decimal points, including, for some reason, this is a casino that can charge you halves of a penny, and 3 amounts instead of 2. And it wasn't the halves of the penny that threw it, but here we give it to it again, and it's off by $2,000. So this is also pretty typical. It's well understood that arithmetic is something that large language models are inconsistent about, particularly as the problems get bigger. But let's sort of press on to more interesting kinds of questions that are more economic and less like the kinds of problems that people have studied in the past. So we say, given your bad luck, you decide to switch to the slots. Slot machine A costs $25 per play and offers a bit more than an 80% chance to win. Slot machine B has a different cost per play and a different chance of winning, and a different reward if you win. Which slot machine should you play? So we give this to GPT-4 Turbo. In this and most other examples that will follow, it just blathers on to no end to solve these problems. So I'm going to have to condense the text to make it fit on a slide, but trust me that you're not missing anything exciting in the gray parts. But at the end, after it gets itself all sorted out, it indeed makes the calculation and knows what to do. So again, evidence that this kind of thing is not insanity, to think that a text in, text out language model, completely general purpose, trained on next token prediction, and then with some alignment afterwards, can actually turn out to be a von Neumann Morgenstern utility maximizing agent under the right circumstances. But again, we see fragility. So now let me ask it fundamentally the same question, but now in the context of a question about the job market rather than a question about casinos. So now I say, your phone now buzzes with 2 job offer notifications. Job P offers 1 salary with no chance of a bonus. Job Q offers a slightly lower salary, but with a pretty big chance of a moderate bonus. Which job should you choose to maximize your expected utility? And here GPT-4 Turbo does pretty well, but doesn't quite get it. So it computes expected utilities correctly, but then eventually it makes the comparison backwards and ends up saying that we should choose the wrong job. This again is pretty typical. We saw getting much of it right and then kind of faltering at the last minute. It happens quite a lot, and we saw consistently that job market problems were hard for it. And we're not sure, but we're pretty sure that this is an alignment issue, that it's much more cautious about what it says about jobs than what it says about casinos. So we found really variation in domains could make a big difference during its competence. I see Craig is already itching to ask a question, which is awesome because I love you guys to ask questions. So we're going to use Craig as an example of what you should do.
Okay.
Go for it.
Cool. Thanks, Kevin. Did you try changing it to, instead of your expected utility, and asking instead what your expected monetary reward should be? So those are different notions.
That's a good point. In this particular case, I didn't, but we framed the question the same way across a bunch of domains, and it was only in this case that it did badly. I gave this talk to a bunch of economists in Switzerland like 4 days ago, and somebody asked me the same thing. I haven't had time to rerun our 100,000 experiments on GPT-4 in 4 days. But get off my back, people. I'll do it. It's okay. Cool. So yeah, somebody else.
Sorry, a late question. Do you have evidence that there would be much more instances of casino sample that you find online opposed to job search?
The question, for those who couldn't hear it, is do I have evidence that there are more casino questions online than job search questions? Could well be. Obviously, I don't have evidence in the sense that I combed the entire internet and counted how many of each there were. But but behind the question, of course, is something I think we all realize, which is, these models are going to be better at things they've seen more of in their training data. And as we vary domains, we might well expect to see variations in how much they've seen. I guess my point here is going to tend to be less to kind of explain exactly why these things are happening, which I think is a bit of a fool's errand, and a little bit more just to kind of uncover what's going on. So I think the important thing I think is that if you really understand von Neumann-Morgenstern utility theory, you're not going to feel like this is an especially different problem. So I think it shows that the reasoning is a bit more superficial than we might hope. Yeah.
I was just wondering if people who chat online about casino talk about expectation, and people who chat about the job offers don't.
I mean, anything's possible, right? If you look at the way that this text actually develops, though, it does get the two salaries right. And then it ends up arguing that I want the lower salary. It could be that it thinks that I have a utility for minimizing my salary, and it could be that it doesn't understand expectations. But it could also be that it just kind of struggles with multi-step reasoning, and that it's particularly kind of paying an alignment tax on job market problems.
I just think that the utility might incorporate risk aversion.
Risk aversion.
Exactly.
Yeah, that could be. Yeah.
Sorry, in response to the risk aversion remark, though, no matter whether you get a bonus or not in job Q, you're guaranteed to take in less at the end of the year than in job P, right?
Yeah, Amy.
Okay, I'm a little dyslexic.
I'm not
I read
sure, so I'm gonna
96,
have to
584, but that's what I was looking for because it said. Yes, okay.
It like similar questions in the sense that it has the same arithmetic, but it's just phrase, one is phrased for jobs and the other is phrased for casino.
Yeah, it's like I have a whole talk prepared. No, I indeed do. This is a motivation slide. This is not my results slide, just so you know. This is just trying to set up what we're aiming to do. And in the end, spoiler alert, we showed I think 4 million questions to each of 20 different LLMs, and it did this, to statistical significance. So this is really just meant to kind of tell you the kind of thing that we did. Sorry, I'm not trying to beat up on you. I just can't stop myself.
Did all the questions you asked have a right answer?
Yes, that's important. So we set this up. Again, we're anticipating a little bit, but I invited you to do it. So we set these up to be multiple choice questions, which is a common practice in the design of benchmark data for LLMs. And we set it up so that there was a desired answer. Not the way that I'm showing you, I guess, in this description here, but ultimately when we get to our results. Okay, but despite this somewhat sporadic performance, I'm still going to push for harder and harder things. So the next thing we might ask is more game theoretic style reasoning. So here I say, back at the casino, you see an open table and sit down to play. You're against one other player, and you have the hand ace queen. They have the hand jack king. You estimate that if you play an ace and your opponent plays a jack, you'll get one amount and she'll get another amount. If you play an ace and your opponent plays a king, she gets something, you get something. What's your opponent's best response if you play your ace? So not tricky. I'm not asking it to form beliefs about what cards the opponent has even. This is like open hand poker. I'm just asking them to think about best response. And GPT-4 does not distinguish itself with glory here. The best response to the opponent is the action that maximizes their payoff. Good job. In this case, if you play an ace, your opponent's best response is to play a jack because it yields a higher payoff compared to the other payoff. That's just not true. If you look at the numbers, we consistently saw problems with asking about best responses, particularly from the opponent's perspective. I'll show you more about that later. Once more, pressing on despite the problems we've already seen, the last thing we're interested in is whether they can make social decisions. So here we say, growing disgusted with your continual string of losses, you joined a petition supporting a ban on casinos. You're put in charge of tallying the votes, and like any sensible person, you decide to use Borda. During the election with 4 candidates, I'm not sure why banning casinos needs 4 candidates, but that's the way it is. You get all of these votes. Who wins if you use the board account? And GPT-4 Turbo, as is often the case, kind of sets up the problem sensibly. It understands what the board account is. It uses a lot of text to kind of set it up, and it gets the answer wrong. Okay, so that's my preamble. So now let me, or that's sort of my motivation. Let me now say, when in working with large language models, if there's a domain like this that you want to have confidence in, and you're forced to do nothing but work with a black box, then benchmarking is kind of the way to go, right? We can't open up the box and see how well it reasons as an agent. So we need to make a benchmark, and this is a long-standing approach in NLP that has lots of positive impact. So here I'm giving you examples of some of the most widely impacted benchmarks. And one thing that's worth saying about these benchmarks is people tend to use multiple choice questions because they make auto grading kind of straightforward. So you can do this stuff at scale. And it's likewise, so will we. And there's really very little out there that focuses on benchmarking for decision making. We were able to find a handful of examples that I put here, including Horton, which is maybe the closest to what we're seeking to do. But each of these benchmarks is really very small. They contain between 2 and 5 tasks. And in contrast, we're going to really want to be much more comprehensive in thinking about agency. So how do you get more comprehensive rather than just kind of coming up with a few little benchmark examples off the top of your head? Here we wanted to turn to economics because it seems to us that economics has spent a lot of time thinking about what constitutes rational decision making. It has a very quantitative literature rooted in the key idea that a rational agent is one that should maximize expected utility. Another thing that we thought was really important and useful about this economic literature that we all will be participating in for the next week is that it characterizes quantitatively which settings matter to economic analysis. So it says, for example, that single agent problems and multi-agent problems are fundamentally different in terms of the kinds of solution concepts they admit. It says reasoning on behalf of a group of people is different from reasoning as a member of one of those groups on your own behalf. There are settings in which the theory is prescriptive, where it says things like, here's how you maximize your utility. Here's some cognitive biases that it wouldn't be a good idea prescriptively to engage in. Others identify places where we would need assumptions or extra information to make good recommendations. And then still others, we have impossibility theorems warning us off against trying to make prescriptive claims. So our aim here is going to be to, as we discussed a few minutes ago, it's going to be to restrict to tests where a rational or a focal answer is well defined. So in cases where the prescriptive recommendation is clear, this is going to be easy. So for example, cases where we have axioms, I can ask questions about the axiom and have a prescriptive aim. I can also come up with easy recommendations in cases where there are cognitive biases. So I can say, set up a sunk cost problem or a loss aversion kind of problem and ask the system whether it would make a choice that's consistent with that bias or not. In more ambiguous settings, I'm going to have to more explicitly ask for the behavior, like elicit a Nash equilibrium strategy. So one way or another, my aim in all of these questions is not going to be to try to elicit what kind of preferences the LLM has, because that would make auto grading kind of impossible in scale, but instead to really set up a question where I understand the meaning of the answer. That being said, we're going to leave it to the end user to determine the scoring rubric in 2 kind of key ways. So first of all, we're going to make this really wide range of different competencies that we might want the agent to engage in, but we're going to leave it to you, the user, whether you actually care about all these things. You might not think that border voting is something that your agent needs to support. You might only care about single agent decision theory. So you can come up with a scoring metric that kind of restricts to part of our benchmark suite. You might also want to use your agent as a cheap alternative to doing human subject experiments that doesn't require you to talk to the ethics review board. And so you might want it to exhibit cognitive biases. So you might want to change the polarity on some of our questions and actually elicit some of the biases that we expect from people. Time to wake up. Okay. It's getting real. So here's the kind of big picture of what we did. There's a QR code, if you are interested in playing with this yourself. I'll put it again at the end of the talk, but if you're impatient, you can look at it now. So this is a live web system where you can play with all of this stuff, and it's really a thing of beauty. The great thing about working with AI students is they can write some pretty great code. When I tried this with the economists 4 days ago, the system was down, and the economists were all disappointed. But we checked it. We think it's good now. So let me know. So in the system, you'll see this taxonomy of what we call elements of rationality that are broken down into 4 parts that mirror the kind of 4 topics that I walked you through in the motivation. So the first is foundations. Foundations that ask questions about sort of mathematical primitives that you would need to have access to be able to do this kind of reasoning that aren't themselves economic. So things like arithmetic, probability, optimization, logic, and theory of mind. This is stuff that other people in related work have also studied, but we wanted to kind of put this all into the same framework so that we could trace failures in the higher level competencies back to these lower level problems. And we actually have a kind of directed acyclic graph defined amongst all of our different elements of rationality, asking which more simple things they depend on. So that if you see bad performance on a more complicated thing, you can kind of trace back and see which simple things might also be failing. Then the second one is kind of about decision theory, decisions in single agent environments. It's broken up into decisions in deterministic and stochastic environments, and in each of those kinds of environments, avoidance of well-documented cognitive biases that humans exhibit in those environments. The blue one is decisions in multi-agent environments. So this is kind of game theory style problems, asking about normal form games, extensive form games, incomplete information games, infinitely repeated games, and Bayesian games. And the final one is decisions on behalf of other agents, asking about axioms of social choice, mechanism design, and sort of simple properties of mechanism design. Yeah.
Sorry, I missed, why did you want to avoid the cognitive biases?
Well, we'd like to test whether it avoids the cognitive biases. You know, if I might have cognitive biases myself, but if I'm hiring an algorithmic stockbroker, I don't really want it to exhibit the same cognitive biases that I do. You know, I think decision theories as a prescriptive theory is pretty convincing to me. As I said, you can change the polarity on our questions. So you could say, I want you to fail the avoidance of cognitive bias questions if you feel like you'd actually like to see your agent show those biases.
Or maybe there's some scale. I mean, maybe, well, okay, we can talk about it afterwards, but I guess I'm just.
I mean,
I had
that's
in
not
mind
something our system would support, but you can certainly imagine how you might set something like that. I think I saw another hand going. Now we'll keep blazing forward then. Okay, so let me give you an example of one of these. So here indeed is a cognitive bias one. So I'll ask about avoidance of loss aversion. And I can't really read my slide. Let's see if you can read it. Next PowerPoint. Okay. So it says loss aversion is a phenomenon where pain of losing is perceived as more intense as the pleasure of an equivalent gain. So we have this kind of text just describing what it is, which is going to be important later for validation. And then we have, it says here, grade 6 example question. So let's drill into that. So by the way, we have these grades, we just made them up. So we have grades between 0 and 13, which are just kind of our subjective sense of how hard different problems are. So here's what we considered a grade 6 question to be. And this is a kind of hard game problem where it's possible to lose something in a risky way. And here's how we take questions like this and turn them into a large benchmark suite of questions. So we take this and we turn it into a template that looks exactly like this, where we put these placeholders in place of all numbers so that we can supply them later. Then we write some instructions. These are hand crafted instructions for every element of rationality and every domain. So here's saying, please give an example, testing the ability to maximize utility in gambling situations, and then setting up the payoffs in a way that causes it to test for loss aversion. And then we have a systems prompt that says you're an economics research assistant. And then given all of that, we also, then we say, you please look at this template and make a generation. And here's an example of a generation that GPT-4 Turbo makes given this whole pipeline. And we can then make multiple generations using the same prompt and get different examples of these questions, all of which have numbers as placeholders, and then we supply the numbers algorithmically afterwards to sort of satisfy or not satisfy the properties that we're looking for. So yeah, so we're basically using large language models to generate these things. In a moment, I'll tell you about how we validate them. So first of all, I want to tell you that these examples differ in these grade levels that I told you about. So for example, here's a transitivity question, and we can make transitivity questions more difficult by giving them more steps of reasoning. They're still pretty simple, but I can say transitivity between 3 objects is easier to reason about than transitivity between 4 objects. And so I can set up these different gradations of reasoning across the different tasks. And we can also vary them in domains. So here's transitivity in leisure activities versus transitivity in fruits. We can generate different examples in both cases. And we do this in more interesting cases as well. We also have a whole validation pipeline built into the UI where we have something describing for each kind of question exactly what the requirements should be for that question. And then a human can kind of quickly go through looking at randomly sampled generations and verifying that they satisfy all of the properties. So we did a reasonably large amount of random spot checking across our whole distribution. And anything that wasn't, in the very high 90% of accuracy, we threw out and regenerated the question in a different way. But generally, we didn't find it too hard to come up with templates like this that would pass our validation. Then we have to figure out how we're going to take many of these answers so that I could get a large distribution of transitivity questions or whatever, present them to an LLM, and I would need to turn them into a score. We can do that in various different ways. I can say, what fraction of questions did you answer correctly? I can say, what fraction of questions did you answer correctly normalized by the number of questions that were presented to you? That's the one I'll report for the most part here. We can ask about calibration errors, so I can look at the uncertainty of the model's answers in the final layer and ask whether, if it says that answer A should come 80% of the time, is it the case that that is true 80% of the time? And we have a couple of robustness definitions as well. And if you look in our UI, you can see all of our experimental results and play with these different scoring metrics that we didn't use. Okay, so it's getting to be time for me to tell you about our results. So we tested pretty much everything that we could get off the shelf. So we tested GPT-4 Turbo, GPT-3.5 Turbo, and pretty much everything free we could get from Hugging Face. And we looked at 4 different adaptations. So we looked at just presenting the multiple choice question and asking it to give an answer. Self-explanation, where we asked it to blather on and eventually produce the answer as its final token. And we gave it a few shot prompt where we gave it 1, 2, or 5 examples of the question of similar questions being answered correctly, followed by asking it on the final question, and few shot prompting combined with self-explanation. And in all cases, we sampled the answer with temperature 0, which is to say that we chose the token from the multiple choice options that was the one that it gave the highest probability to in the final layer. I should caution you here, from this point in the talk on, I'm going to tell you how all these models did and kind of give you a sort of bake-off. But we don't really see this as our main contribution. Models are constantly changing. There are many ways that we could have prompted the models differently. We could have endowed them with access to a calculator. The models could have made multiple passes through and reflected on their answers. That's a kind of whole research area in LLMs, which is really active. And what we're really aiming to do here is to think about how you would get an answer about whether any given agent architecture does a good job, rather than to argue that this particular architecture itself is doing a good job. So we wanted to be a little bit thorough in thinking about the kinds of adaptations that people have said were important, but this is really just meant to be putting our benchmark distribution through its paces to get some sense of where things stand today. All right. So our curriculum in total consists of 60 elements of rationality across these 4 settings that I told you about. We're still adding actively to this set, so if you have ideas, you want to email me or come up afterwards, we're still interested in adding more things. We've in the end generated almost 29,000 multiple choice question schemas, which we instantiated as almost 1 million test questions. In particular, we generated 1,000 tests for every element, domain, grade level tuple. And we uniformly sampled questions and instantiated the placeholders generically. We've evaluated this on 20 LLMs, each of which with 4 adaptations. The slides only have 14 LLMs because the figures are hard to generate, but the remaining ones don't change the story because they're small LLMs. Okay, so whoops, here's what our pictures look like. So let me walk you through how to read all of this, because I'll show you a bunch of pictures that look like this. So the rows correspond to elements of rationality. So here I'm showing you addition and subtraction and multiplication and division. Each cell represents between 1,000 and 5,000 questions. So all of the questions about that element of rationality that we presented to the LLM, which vary in their domains and in their hardness level. The columns correspond to LLMs, which I'm presenting to you in descending order of number of parameters. So the leftmost one is GPT-4 Turbo, which we don't know exactly, but the smart money says that it's about 1,760 billion parameters. The next is GPT 3.5, which is 175 billion. And then we get into the free models, which are 70 billion, 65 billion, 40 billion, 13 billion, and 7 billion. So you see the kind of indices that I've put at the top. And you see, I put a vertical bar between 40 billion and 13 billion because we see a qualitative change in performance. What do these colors mean? White is random guessing. Shades of red are doing worse than random guessing. Shades of green are doing better than random guessing. And GPT-4 Turbo here looks like it's doing pretty well, but even that dark green is 0.79, so like almost 80%. So it's still not fantastic. So that's how you read these things. So this is arithmetic. This is optimization. So optimizing over a discrete set, optimizing a continuous function, constrained optimization. Then reasoning about probabilities, some kind of simple logical reasoning, and theory of mind, reasoning about false beliefs, both in oneself and in a second party. And so broadly speaking, you see that the number of parameters makes a big difference, that GPT-4 Turbo is the one to watch, that below 40 billion parameters, we're getting nowhere at all. And the broadly speaking things are not great, but not terrible here. Yeah, maybe.
Can we compare across tasks here? Like, does the dark green in different pictures, that I can't read the numbers, so they're the.
Yeah, you can't read the numbers.
Right, so can you tell us, like, is theory of mind, is the number much smaller than in arithmetic?
I mean, I can't really read the numbers either.
Oh, I see.
Like,
Okay.
memorize. But I mean, you can again, you can open up our web app and you can really drill into all of this stuff. It's all there. If you're asking, is theory of mind doing first order false belief doing a little bit better than addition and subtraction? Looks to me like it is. Certainly the case that second order false belief is more challenging across the board for all the models, which is something I'll come back to. You can see that from the colors. Certainly just presenting kind of a qualitative picture here, but we'll drill into some results in a moment. Yeah.
Just like looking forward to the workshop this afternoon on academia, are there relationships between this and like competency-based learning and like just tests for humans as well? Like if I'm just an educational setting, I want to create a test that tests Bayes' rule and how well my students understand it. Is there any relationship between this and that, or could this be used for that, or did you draw?
Why not? I mean, here we're going to multiple choice tests that are very easy to grade and somewhat spotty, in exchange for being able to have really high volume, because it's feasible to ask 5,000 questions on the same topic to an LLM, and the LLM doesn't learn while you're doing it. So you can really do that and get a broad sense of its competency. I don't know about students in Michigan, but I think at UBC I'd have trouble making them sit still through 5,000 questions about Bayes' rule. So it might be necessary to kind of set it up differently for humans, but otherwise in principle, this would work fine. Yeah.
I'm confused about all the red in the chart. You're saying the red is worse than random guessing?
Yeah, I don't get it either.
Okay.
They really just do egregiously badly, but that's something you're gonna see all over the place. Yeah.
And I'm sure you give a very long answer, but just in terms of the complexity, I'll say probability, right? When you say computing based, like how complicated this is? This is like, 3 events or something, 2 or 3 events?
It's all pretty simple stuff.
Really?
I mean, you
Okay.
can, you can again drill into the app. I don't have that memorized either, but
But just qualitatively, these are even the
none of this is very
optimization.
tricky.
What's that?
None of this is very tricky.
Okay.
It's certainly the foundations. Some of the higher order tasks, you're gonna need to know some terminology, although almost always that's not where the big models fail, so. Yeah, okay, so let's go on. So this is foundations, which again is kind of a warm up. So let's get more to the kind of game theory-ish econ stuff. So here is asking about axioms of utility in deterministic environments, cognitive biases in deterministic environments, axioms of utility in stochastic environments. So we just divided up the axioms, cognitive biases that require the environment to be stochastic, and reasoning about risk neutrality, making risk neutral decisions, which was one of the most painful things for us to set up because we have to try to tell it to be risk neutral. We're not trying to elicit its risk attitude. But yeah, that was when I struggled with more. So let me drill into a few of the things that we observed here, a few of the kind of interesting inversions, unless you want to ask questions before I do.
Yeah, so is this across the board because you have your 13 grades? 14 grades?
We typically only have kind of a couple of grades per question. It's more the case that we'll see a whole question as being a more difficult thing to reason about than say addition. So we would maybe have a couple of grades that would be like grade 6, grade 7 or something. But for most questions, we had like at least probably 1 grade level change. Again, that's something you can see in the app, but certainly not the case that we have a huge variation in difficulty within a question.
But for like for transitivity here, right? You gave.
Yeah, so we're averaging across all the grade levels that we asked. Okay. Yeah, so let's drill in. So here's an interesting one. This is avoidance of sunk cost fallacy. You might not eyeball this and think it's an interesting one, but here's a place where GPT-4 Turbo is doing less well than GPT-3.5. So, which is something we don't typically see. So let's look into that and see why that is. So here's one representative example that we saw. So Johan just approved an AI project with an initial investment of 700 million, which is estimated to bring $1 billion in profits. Updates in the technology environment reduce the projected gains to 473 million. Should he abandon the project or update the technology by spending an additional 500 million? And GPT-3.5 correctly says he should abandon the project and prevent further losses. What if we change this to say, should he spend an additional 400 million? Where it's no longer a sunk cost because now he, even in the continuation is going to gain expected utility by continuing to invest. This is the kind of place where GPT-4 Turbo goes wrong on these questions. So it turns out that it's seen a lot of sunk cost questions, and if you show it something that kind of looks like a sunk cost question but isn't, it overfixates on it and refuses to continue investing anyway, even if the numbers work out. So GPT-3.5 was a bit better on that. So this is an example of the kind of thing you find when you look quite extensively that you might otherwise not look for, where superficially there's a lot of evidence that it knows what it's doing, but somehow it still isn't really reasoning coherently. Another thing we found is that it matters whether these questions are phrased in the first person or the third person. So if I say something similar, but now saying you've done this rather than Johan, then GPT-3.5 does a lot less well. So it is much more cautious about decisions when it's going to take the blame than whether it can blame it on Johan. Here's another one. Let's look at this avoidance of endowment effect example that I showed you here. This one is surprising because it's one of the few examples where the small models shine. And even so, the GPT models are struggling pretty badly. So what was going on there? I guess I have these sort of overview things. I'll say them before I show you the example. It'll make it easier to follow. So the GPT models can exhibit a strong endowment effect when they're told what their preference is supposed to be, and then asked to reason from that preference directly, whereas the small models were able to handle that. The big models are much more consistent when we also elicit the first preference from the model. So yeah, way to go, baby models. So let me show you an example of this. So we say last year you were at a family picnic where they gave away sunglasses and baseball caps. You got a pair of sunglasses. Your cousin received a baseball cap and proposed a trade. You declined. That's the part where we're specifying the preferences. You've lost those sunglasses. The same situation is happening this year, but this time you got a baseball cap. Your cousin received sunglasses and proposed a trade. Do you agree to the switch? So GPT 3.5 Turbo says something that doesn't make a whole lot of sense to explain why. But if we set it up this way, where we just bring it up and we ask whether it wants the first switch, it expresses that it has a preference between the two of them, and then it gets it right. So that was kind of representative of what we saw on endowment effect, which we only saw this behavior from the large GPT models, and nobody else had this strange instability. Yeah.
So, I mean, probably there are a lot of questions like this, but at least for me, it seems plausible that you've realized that you're gonna lose your sunglasses, so now you don't want them again, right? Like, so maybe the fact that the smaller models do better on this one question, it makes me prone to question whether the answer is actually right, or whether maybe the answer from the larger models is plausible.
I mean, I guess, we're seeing here persistently that with word problems, it's always possible to tell it, or it's often possible to tell a story to try to salvage, why the thing maybe would have done something sensible. I guess that's possible. I can say, I see no evidence in the text that's generated that it of this kind of creative reasoning. When we've spot checked answers that say something like, having lost my sunglasses, I now update my preferences and realize these things are useless to have because I lose them immediately. But a baseball cap is something that's big enough for my meaty hands to hold on to it. I guess if we saw something like that, we would be impressed and we would maybe change the question. What we read is just a lot more incoherent than that. But fair enough. All the same, we see that as variation between models. Okay, let me keep going. So here's, I'm moving on to the multi-agent setting, and you see the board is starting to get less green. So here's reasoning about normal form games, reasoning about extensive form games, incomplete information, infinite repetition, and Bayesian games. And by and large, this is just stuff where the models are doing a lot less well. Let's drill in a little bit. So let's look at best response, where you see GPT 3.5 really struggling here. This was really evidence of what I was mentioning to you a bit earlier, that these models have consistent weakness in reasoning about others. So they do very much better in reasoning about their own best response to somebody else and somebody else's best response to them, which are, of course, mathematically equivalent problems. And tracing back in this kind of hierarchy down into the foundations, we found a similar degradation in performance on second order false belief versus first order false belief for the same models. So here's just kind of quantifying that across all of the models. Here's looking at best response when asked to choose the best response for oneself versus when asked to choose the best response for the opponent. And you see in particular, GPT 3.5 Turbo was really outliingly bad at reasoning about the opponent compared to the other models. But for everybody, there was a marked decline in reasoning about one's own best responses to the opponent's best responses. And when we look at second order to first order false beliefs, let me just give you an example of what that looks like. So the second order false belief is the ability to identify beliefs that an agent has about what another agent believes that are different from the truth. So Sarah places a book on the kitchen table and steps outside to play. While she's gone, her friend Marcia picks up the book from the table and puts it on the bookshelf. When Sarah returns, where will Marcia think Sarah will search for her book? And GPT 3.5 Turbo says something incoherent. Marcia, who moved the book, knows the new location she placed it in, so she has no reason to think that Sarah will look for it in its original place. But first order false belief, a container of ice cream is left out on the counter, but instead of ice cream, the container has been filled with mashed potatoes. The container is then put back in the freezer. What do you think your cousin will think is inside the container? They might think something along the lines of, why are there mashed potatoes in the ice cream container? Or this isn't ice cream, because that's not what they anticipated finding. So much this is again is represented, so much more consistent answers on the first order questions. Finally, something that's well known in the LLM community, but worth mentioning, is that LLMs beyond game theory just struggle to reason with tabular data. It's an active area of research and a place where the models are getting better, but it's still a speed bump for them. And so it's difficult to describe any kind of game situation, even a pretty small game, without having some kind of tabular representation of the data. And that's kind of an additional difficulty for the models. So we can see just ways that the tabular data itself is causing the model to struggle. Okay, so then we get to economic decision-making on behalf of others. And I won't drill in here, but just to show what those results look like. Again, we see on the ACM questions and the property questions, they do all right. But again, certainly not a place with strong performance. And even for GPT-4 Turbo, it's getting scores of like 0.25 or something in many of these questions. So still an area where there's a lot of improvement to be made. In terms of those adaptations that I told you about, the self-explanation adaptation, unsurprisingly, was always helpful. So everything I'm showing you is with self-adaptation. Few shot prompting helped when we moved from 0 to 1 and 1 to 2 examples shown in the context. And we actually found a small but significant degradation in performance, moving from 2 to 5 examples. So the results I showed you were with 2. And no model did consistently better than random guessing past our grade 9 questions. Our questions go up to grade 13 because I'm from Ontario and I had to go to grade 13, so I don't see why the models shouldn't have to as well. Okay, so that's the end of our ICML paper and the archive paper that I just told you about. We're continuing to work. And I have some new slides that are new as of late last night that I'm going to very quickly tell you about what we're actively working on because it's fun. So, and if you are interested in learning more about this stuff, too bad, there's no way to find out more because we haven't put any of this online. So everything I've told you about before kind of looks at microeconomics in strategic settings. In the sort of AGT kind of course pipeline, like the Coursera course that I was involved in, where you have to think about best response, Nash equilibrium, and so on. A lot of microeconomics isn't really about this kind of strategic reasoning. So a lot of a kind of straightforward micro curriculum looks at supply and demand, production and supply costs, consumer and producer surplus, regulatory impacts on surplus. So lately we've been collaborating with Jesse Perla, who's a macroeconomist at UBC, in trying to set up a broader set of questions that would kind of steer to the kind of full micro pipeline. And so we're now kind of extending all of everything I've shown you before into sort of non-strategic questions that think about price-taking consumers, firms too small to be market movers, and regulators who want to look at a market equilibrium. So here's the taxonomy that I showed you before with the number of questions in it. And we now have a taxonomy that looks like this, where we've substantially extended the foundations to have a bunch of new foundations and added 4 new categories that focus on these different questions in micro. So in foundations, we've now added a bunch to optimization and added a bunch of new foundations on derivatives and systems of equations. And our new topics look at consumption decisions in non-strategic environments, production decisions in non-strategic environments, non-strategic decisions in multi-agent environments. So thinking about kind of market prices and equilibrium, various kind of market equilibrium notions, and evaluating equilibria and externalities. And for each of these, we have more elements of rationality than we had in any of the ones before. So this whole area of economics is much more mathematically focused with an emphasis on calculus, which can make the setup of questions pretty tedious. So we often have to instantiate a utility function in a class of good and kind of do a big setup before we can get to the questions. But undergraduate economics students can handle it. We think LLMs should be able to handle it too. The mathematical emphasis here allows us to do much more fine-grained scoring when we look at these numerical outputs. So we can ask questions like, when we give you a question that ought to have a positive derivative, or I guess I wrote it the other way, if it ought to have a negative derivative, it's a worse thing if you give a positive derivative than if you give a wrong negative derivative. So we can have more fine-grained scoring in that kind of way. So let me give you just a couple of examples of what this looks like. So here's a question about Marshallian demand that says, imagine Sarah enjoys two main activities, reading books and drinking coffee. Her satisfaction or utility from these activities can be modeled by this utility function, square root of x plus square root of y, where x represents the number of books she reads and y represents the number of cups of coffee she drinks. Sarah has a monthly budget of xp sub x plus xp sub y, where the prices of books and coffee are denoted by px and py respectively. Given her income and the prices of books and coffee, what is Sarah's demand curve for books? So GPT 3.5 Turbo, we give it all of this, is not quite able to get it done just because it struggles with the algebraic manipulation. But GPT 4 Turbo is able to do pretty well. So it actually sets up the Lagrangian, solves the equation and simplifies it and gets the answer right. So this is not beyond the realm of possibility to be studying with LLMs. Here's a question about marginal consumption. So imagine a factory that produces widgets where the production relies on two key inputs, labor and capital. In this context, let's say labor is represented by X and capital by Y. The factory's output is determined by the Cobbs-Douglas production function given here. If the factory employs 4 units of labor and uses 9 units of capital, what is the additional output produced by an extra unit of labor? So again, GPT 3.5 Turbo, has many of the right ingredients, but doesn't get it right. But GPT 4 Turbo, besides calling it the Cobb-Douglas production function, otherwise nails it, and goes all the way through the analysis and gives us the right answer. So again, not beyond the realm of possibility to be hoping for, but getting pretty close to the cutting edge. But only up to a point. So if we make things a little bit more complicated than that, this is my last slide. So here's a question on comparative statics of equilibrium prices with shock. Suppose a firm has a production function of the form Q equals A, L to the A, K to the B, where Q is the quantity of output, L is the quantity of labor, K is the quantity of capital, A is the constant representing total factor productivity, and A and B are the output elasticities of labor and capital respectively. Suppose the initial equilibrium prices of labor and capital are W and R, and the initial productivity is A sub 0. Now suppose there's a 20% increase in the price of labor, while the price of capital remains constant. Assuming perfect competition and that all other factors remain constant, what happens to the equilibrium price of the output? So GPT-4 gets off to a good start, but at some point starts garbling things and can't recover, ends up saying that the optimal quantities of both labor and capital are both 0, which is pretty nonsensical and entirely different from the right answer. So not meaning to say that this thing out of the box is a microeconomic wizard, but certainly the case that this stuff is worth studying. So we haven't yet gotten to the point of being able to run the comprehensive experiments here. So this is really hot off the presses, but this is what we're currently thinking about. So I'll leave it there. So I've told you about how we might benchmark the use of LLMs as decision-making agents, varying application domain, difficulty level, and the way we score them. We have the whole thing supported by a flexible web interface that you can play with, and we've done some extensive experiments. Here's where you can find our archive paper and the web interface if you're interested in playing with it yourself. Thanks for your attention.
By the way, great stuff. I really like this. One thing that you didn't quite get at, but there was a hint of it in the way you framed some of those later questions, was causal factors and confounders and all this type of stuff. So I'm drawing a blank on the name. Somebody wrote this paper. They were looking at earlier models than this, but looking at price elasticity and can you actually generate demand curves, and it would get it all up. Whatever it was, GPT 3.5 at the time was all over the map. They just had to frame things and say, hey, if I raise the price of Coke, what happens to the demand? And it would eventually kind of get the demand curve in the right shape, but not nearly steep enough and so on. But then they would ask it to explain why, and it will come up with all kinds of weird, wonderful explanations, because maybe the price of Pepsi went up as well. Do you get any of this here? I mean.
We haven't pushed on that as hard of like, given that we're doing it at such scale, we've really mostly spot checked patterns that we find surprising. So I think there's a lot more to be dug into to try to get these kinds of explanations.
Yeah.
So
Because.
the short answer is mostly not, I think. Yeah.
So
Start plugging and changing things.
So you measured the ability of LLMs or the propensity of LLMs to give the correct answers on these verbal questions about economic reasoning, which I think is really neat. Also, I think Elements of Rationality would be a great book that I wish existed. But I guess what I think the conclusion that I don't want to necessarily draw from this is that this means that they, in some sense, aren't capable of kind of utility maximizing reasoning, right? Because there's this is the querying them for these explanations is kind of obfuscate the actual expectations of the predictive model, right? It's trained to predict what humans would say on this kind of question, but it's not necessarily motivated to give the utility maximizing answer, or to give you the correct probability calculation. But if you gave it some sort of actual sequence where you could observe like the regularities in the sequence had some, and it could learn the probabilities and do Bayesian updating on the sequence, then you could look at the actual token level probabilities. You could see if it was doing Bayesian updating, right? So there's kind of two different levels of explanation.
I'm not entirely understanding how to turn that into a question. Maybe it's not a question.
Do you think that do you think this means that the models don't understand Bayesian or don't understand utility maximizing behavior, or do you think that it just means that they aren't necessarily displayed? Like, are you confident?
I guess, like, as I said before, I don't think our experimental results should be read as a definitive statement about whether or not models understand these topics or can do them. I think instead this benchmark distribution constitutes a way of asking the question about any kind of full agent architecture, which would include the prompt, the way of reasoning across probabilities in the token stream, everything. So I think if you want to propose, oh, that's just trying to imitate people, but hey, if I do something differently, maybe then it would really be an agent. I think we've built something that we think you could use to figure out whether you're right. And that's really as much as I would want to claim about what we've done. So I think these initial results are kind of suggestive of the kinds of answers you could get, but I think a simple prompt just running on top of vanilla GPT-4 doesn't look like a good way to build an agent. I don't think that's the way you would want to do.
Right, and I am trying to build such a thing, and I will use your benchmark.
All right, well, let us know how it turns out. I'm going to keep answering questions until somebody shuts me down, which might be now.
Yeah, we started 5 minutes late, so yeah.